The lab determining an equilibrium constant has a couple different parts to it and quite a few calculations. So I wanted to walk you through some of the background before you come to lab. The first thing we need to review is Beer's Law. If you remember, if you were in class last semester, we did a whole lab on Beer's Law and determining the concentration of a cobalt solution from its absorbance. Beer's Law says that absorbance is equal to K, the Beer's Law constant, times the concentration. We are going to be using 450 nanometers because that is where the iron thiocyanate complex absorbs the most. And so what we can do is we will collect a series of data points, and we're actually going to use equilibrium for this. So we are going to essentially, here's our equilibrium equation. The iron 3 plus thiocyanate goes to the iron thiocyanate complex. And we're going to be using a very dilute thiocyanate and lots of the iron 3. What's going to happen is that's going to shift our equilibrium essentially all the way to the product side. And so we can assume that our concentration of our SCN minus, which we can calculate from the table 14b.1 on page 177, is equal to our equilibrium concentration of our iron thiocyanate complex, which is red and absorbs at 450 nanometers. Then what we can do is we can put our concentration of our iron SCN 2 plus, and our x-axis and our absorbance, which we will get by putting the solutions into cuvettes and reading the absorbance at 450 nanometers. I will show you how to do that in lab as a reminder, or if you haven't used this before as a demonstration. And we will get, let's see, we have 5 test tubes. You can assume it goes through 0, 0, 1, 2, 3, 4, 5. We'll get a series of points. Then we can do a best fit line through those points. And maybe a little bit lower. You can, in doing a best fit line, you can either do this on the graph paper provided in your book, or you can use a program like Microsoft Excel to graph, and then that will calculate a best fit line. Or if you know how to do that on a graphing calculator, you feel free to do that. So we're going to get a line. Remember, lines are in the form y equals mx plus b, but we're through 0, 0, so our b is 0. And our m is our slope, which is our k. So you see y equals mx plus b is the same form as a equals kc. And you're going to need that lowercase k, that Beer's Law constant, in order to calculate the concentrations to get your equilibrium constant. So the first part of this lab, you're making solutions, driving your equilibrium to the product side, and then using the concentrations and the absorbance to make a graph, and finding that K value is the goal. If you look at your post-lab, question 1 has you calculating that iron thiocyanate concentration. You can do that using M1V1 equals M2V2, and that table 14B1 on page 177 that I referenced. And remember that concentration there, what I wrote here, you can assume that the equilibrium concentration is the concentration of the thiocyanate because there's so little thiocyanate and so much iron. And then the A is just from the previous page where you wrote down the data. So you don't have to do any calculations for A there. You're just transferring from page 181 under 1, obtaining data for determining K, transfer the data over. So that is the first part of this lab, kind of the first big concept is you need to use Beer's law to get K. The second part of the lab, next page, there we go. You are going to be determining, your overall goal is to determine capital K, the equilibrium constant, which remember is going to be your products over your reactants. C and minus. There we go. Question 2 in the post lab works you through the steps of how to do this. And so I am going to go through each column in that big table. I know yours is going to go, it has more than the 9 test tubes. It goes down to 15. But I'm going to work you through each step in determining that K value. So the first column is the starting iron concentration, and this is another M1V1 equals M2V2, and that's actually both the starting iron and the starting thiocyanate concentrations come from M1V1 equals M2V2. The table for that is table 14B.2 on page 178. So you can simply find the total volume for all of them should be the same. You're given the starting concentrations of both of them in the top of the column. The starting volume for each test tube is there. Your final total volume looks like is 7.0 for each. We've had plenty of practice doing that. The next column is your equilibrium concentration of the iron thiocyanate complex. There, you're going to be using the fact that A equals KC. You will have, for all of these test tubes, determined an absorbance value. The data for that will be on page 181 at the bottom. So you made all of these test tubes, you put them all in the spectrophotometer, found the absorbance. The K value you just calculated in the first part. So that graph that you made that I just went through on the previous page, and then C is what you're looking for. So you can take your absorbance value, divide it by your K, that will equal your C, which is your iron thiocyanate. Then you need your equilibrium values of your iron 3 and your thiocyanate. There, you can just do an ICE table. So here, let me write both of these. You're going to be doing an ICE table. So you know your Fe3 plus SCN minus is in equilibrium with the complex there. You know your starting of both of those. Those are those first two columns. And now you know your equilibrium concentration from there. And so you can, that ends up being your X. And it starts at 0. So you can figure out your equilibrium concentrations. So known minus that X value. There's no coefficients, so it's a pretty straightforward ICE table. I only need to see, you can see at the bottom of page 184, it says representative calculation. So I only need to see one calculation. So if you just want to do, show me the calculation for test tube 6, and then for the rest, if you need to write it out, you can do it on scratch paper. If you are unsure of, working through this, go ahead and do it on scratch paper and turn that in. I'm happy to look it over for you if you're not sure about it. If you're like, oh my, I am doing this same thing 10 times in a row, I don't need to write all this down, feel free. I just need to see a representative calculation, not the whole thing, because as you go into this, you'll see a pattern that you're doing the same thing over and over. Then your K value. Now you know everything. You know comes from these 3 columns, go into that K from this equation up there. Your K values should all be pretty similar to each other. That's why at the bottom it says mean. That is your mean K value. And then 2B on page 185 says determine the precision of your results for K using the method shown in Appendix A. You don't have Appendix A, but you can either use, I will put a link up for a website that will get you standard deviation, or again, if you know how to use a program like Excel, you can get a standard deviation from there. And remember your standard deviation, so you'll have some value for K, and then it'll be a plus or minus, and your standard deviation is only 1 unit or 1 value. So if your K is 125, it's going to be plus or minus, 6. Where this digit is and where this digit is need to match. If it's 100, or let's do 1,050 plus or minus 30, something like that, so that your error here and your error there are in the same spot. If you have questions about that, please let me know. I can explain that more. We went over that towards the beginning of last semester in lab.